All right, so here we go. We're going to talk about in these two sections that we pick up in chapter 8. They may seem sort of random, like just randomly placed. They are a little bit, in my opinion, but maybe not 8.4. But this one, section 8.2, we're going to talk about indeterminate forms of limits. And L'Hopital's rule. And that's how you spell that. He is a French mathematician, yes. That's an H. This is an H. I can't remember off the top of my head. Okay. What? L'Hopital. This is L'H for those of you that are French learners. Okay, so tell me the indeterminate forms of limits that we talked about way back when.
Like indeterminate.
They're not
continuous.
They're not
When did we have to do more work?
Zero.
We got 0 over 0. Okay, when we got 0 over 0, that is the that's the indeterminate form of limits that we encountered most often, was that 0 over 0 thing. And you guys learned to say that we would have to do more work, right? And what were some of those other algebraic techniques that we learned? Factor and cancel.
Multiply by
Yeah, multiply by conjugate, right? Multiply by conjugate to get rid of radicals. Get a common denominator if we were dealing with compound fractions. Use trig rules if we had some trig stuff going on. So all of those were different things that we did when we encountered 0 over 0. So these are indeterminate forms of limits. 0 over 0. Infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to infinity, and infinity to the 0. Those are all considered indeterminate forms of limits.
But so, well, zero to the power of 0 would be 1 to something.
No, it's an indeterminate. Yes.
Anything to the power of 0. Except 0.
One raised to infinity and then 1.
0, 0, 0, 0, repeating, and then a 1 at the end. So the power of 0. That's a 1.
Okay, so in this particular, I don't have time to debate those questions right now, so we're going to have to keep moving forward. Okay, so if I were to plug -1 in right now, what would I get?
0.
I would get 0 over 0, right? And I would have to do more work. Okay, that is what I would have to do. And so this produces 0 over 0. Okay, so for my do more work, this now becomes the limit as x approaches -1, and what would you do?
Separate the 2 times x.
Factor out a 2 in the numerator, and that leaves me x squared minus 1 over x plus 1. Can I plug it in yet?
That can be reduced to x plus
No.
No. If I plug it in right now, I still get 0 over 0. But the numerator can be factored. And then what happens? Those cancel. Now can I plug it in? Yeah, and what do we get? Negative 4. This is review basically. Okay, let's look at another one. Let's do the limit as x goes to infinity of 3x squared minus 1 over 2x squared plus 1. So what do I always try first? Direct substitution, right? And if I were to do direct substitution here, what do you get? You get infinity over infinity, right? Some form of infinity over some other form of infinity. Okay? And what did we say you could do in that particular situation? You could check your highest agreed terms, right? And if my highest agreed terms were the same as they are here, what is the answer? Yes, those are the same, so I get 3 over 2. And let's look at one more. I'm leaving space here for a reason. Okay, we're going to come back and look at some L'Hopital's here. Bless you. Okay? So if I try direct substitution there, what do I get? Right, this gives me 0 over 0, right? But Shelby reminded us of a technique that was called what? Okay, so I would multiply both top and bottom of this thing by minus 3, right? Because now in the numerator, what do you get?
Wait, is that first one?
First one's minus
Yeah,
3.
then you change it.
Plus.
It should be minus 3.
First one it's minus
Oh,
3.
my bad. I see what you're saying. I did. When I rewrote it, I wrote it with a plus already. So that's minus, so that means these are plus, right?
Yeah.
Okay. So I get x plus 2, my inner and outer term, inner and outer go away. That's the whole point of multiplying by the conjugate, right? And then I get what here?
Negative 9.
Minus 9. And then on the bottom, I just have this whole thing left, right? The x minus 7 and that. What's the numerator change to be if I simplify it?
X minus 7.
That's x minus 7, right? And then what happens with the x minus 7s? They cancel, so I have 1 over all of this. Now can I plug in? And what do you get?
1 over 6.
1/6, right? Okay, so those are all of the techniques that we used when we were first learning how to do limits, and direct substitution yielded the form 0 over 0 or infinity over infinity. Okay? Well, the good news is that there's something better, and you don't have to use that anymore. Okay? If you get 0 over 0 or infinity over infinity, you can use something called L'Hopital's rule. Okay? So, let's get this in here. Not all indeterminate forms can be evaluated using algebraic techniques. So we use L'Hopital's rule. I'm going to give you the rule. We're going to go back and work those three limits using it, and then I'll show you a kind of a proof as to why it works. Okay. So here we go. If the limit as x approaches a of f of x over g of x, if the limit as x approaches a of f of x over g of x results in 0 over 0 or plus or minus infinity over plus or minus infinity, then the limit as x approaches a of f of x over g of x is also equal to the limit as x approaches a of f prime of x over g prime of x, provided the latter exists. Latter, yeah. Okay, so in other words, if I go and I do a limit problem, and by substituting in a to this function over this function, it gives me 0 over 0 or infinity over infinity. L'Hopital's rule says that you could do this whole limit again, but instead of making it f of x over g of x, do it with f prime of x over g prime of x. Okay, so go back to the first example that we did. If I plug -1 into this, I get 0 over 0, right? Okay, well, L'Hopital's rule says that that's equivalent to the limit as x approaches -1 of the derivative of the numerator. What is the derivative of the numerator? 4x over the derivative of the denominator, which is 1. What's the answer to that?
Oh my gosh.
Oh, wow.
-4.
Derivatives all over the
Oh my goodness.
Yes.
Will this work for
Okay, the question is, will this work for all? Okay? It works anytime you do a limit and when you first try evaluating the limit, it gives you 0 over 0 or infinity over infinity. Okay? So take a look at the next one. Now the next one, the ones that involve infinity, they're pretty easy when you just think about the powers, you know. But you can see how it works. Okay? So it gave me infinity over infinity. So L'Hopital's rule tells me I can do it again by taking the derivative of the numerator, which is 6x, over the derivative of the denominator, which is 4x. But what does that give me? That still gives me infinity over infinity. So I can do it again. I can do it as many times as necessary. I can do it as long as I'm getting 0 over 0 or infinity over infinity, I can continue to use L'Hopital's rule. So this would be then equivalent to the limit as x approaches infinity of, what's the derivative of the numerator? And the derivative of the denominator?
4.
Which is just 3/2. Okay. Now that one, clearly this is pretty simple. If the highest degree terms are the same, just look at them. But I wanted to show you, A, that it still works, and B, that you can perform or you can utilize L'Hopital's rule as many times as you need to. Okay, so let's take a look at the last one. Clearly that gives me 0 over 0. So what is the derivative of the numerator?
1/2.
1/2 x plus 2 to the negative 1/2. And what's the derivative of the denominator? 1. So this is the same as that, right? Which is
1/6.
1/6. Okay.
Thank you, L'Hopital.
Yes. So L'Hopital is a good man. Okay. So let me kind of give you the verbal explanation of why this works. When you're doing limits, we'll take one that where you would get infinity over infinity. Okay, so like the second one. What you know is both functions are approaching infinity, right? Like if you plug infinity in the numerator, it's infinity. If you plug infinity in the denominator, it's infinity. So individually, those functions are approaching infinity. The question then becomes, okay, but how fast are they approaching infinity? Because if I can figure out the rate at which they're approaching 0 or infinity, then that gives me more information. So when I take the derivative, right, of this one, and I get 6x over 4x, well, now I'm back to infinity over infinity again, right? But again, the question is, how quickly is one getting there over the other? And whenever you're taking the derivative, you're examining the rate at that point, okay, or at that value. So that's sort of a verbal explanation. And I can give you, because I'm assuming there are enough of you in here that are brainiacs, you want to know why this works. If you don't want to know why, then you can sit there and vegetate. And if you do want to know why, I'll show you. I'll give you a mathematical.
We're never gonna like.
No, you don't have to do this or anything. You can just watch it. Okay?
Sanders,
Yes.
do you have time to eat a piece of chocolate right now?
Do I? I'm going to hold off for a minute. Thank you, though. Appreciate it. Okay. So I'm going to start with this. I'm going to work backwards. Okay? So I'm going to start with derivative of f at a over derivative of g at a. Okay, that's what I'm going to start this thing with. And I am going to write the formal definition of each of those. I'm going to write an equivalent statement using their formal definition. I'm going to do it at a point. Do any of you remember what that is, by the way? Definition of derivative at a point.
I'm just subtracting a at f of a plus h, a minus.
Okay, and you know what? Derivative at a point. You're on the right track. You're giving me the general definition, the formal definition of derivative in general, and I want to know it at a point, f prime of a. Any of you remember that?
Instantaneous rate of change.
It's like the first thing I did. Oh.
Right?
I remember it.
Okay, that's fine. Even if you look at it now and see it, this is, if you see this right here, this means what's the derivative of f at a? That's formal definition of derivative at a point. Okay, so all I did was take this. I'm working backwards here. F prime of a can be defined by the limit as x approaches a of f of x minus f of a over x minus a. Yes?
On L'Hopital's rule, does it work with derivatives that repeat, like e to the x and sine and cosine?
As long as If initially it produced 0 over 0, then yes. Or infinity over
What if
infinity.
it keeps repeating, so you always get 0 over 0 or infinity over?
I'm going to show you a logarithmic trick here in just a minute, and that might answer your question. Okay? All right, so what would I write here?
G of X
G of x minus G of a
G X minus
all over x minus a, right? Okay, so then my rules for limits tell me that I can do what now with these two separate limits? I could make it one limit, right? I can make it one limit. I can make it limit as x approaches a of all of this mess. Right? Okay, so dividing by a fraction is the same as multiplying by the reciprocal. So now what happens? What am I left with? F of x minus f of a over g of x minus g of a. I forgot to give you an assumption. Here, let me put it up here. I'm not going to be able to squeeze it in. F of A equals G of A, which is equal to 0. F of A equals G of F, equals G of A, which is equal to 0. So now what happens to F of A and G of A? They are 0, right? So that is equal to that. Okay? And that's really, it's not all of the proof, because you do have to end back up with these limits here, but it's kind of beyond the scope of our course. But hopefully between this little bit of algebra and that idea of understanding, if I can figure out the rates of both the numerator and the denominator, how quickly one's going toward infinity or 0 and the other one, hopefully that makes some sense out of it for you, okay? Basically, you need to know we're going to use L'Hopital's rule to find answers to limit problems when the original limit produces 0 over 0 or infinity over infinity, okay? A very common error, okay, listen up, so you clue in. Very common error people make when they use L'Hopital's is they use the quotient rule. Have I used the quotient rule any of the times I've utilized it? No. Remember, it's the derivative of the numerator divided by the derivative of the denominator. There is no quotient rule involved here. Okay? So don't make that error. Okay. So let's do a couple of examples because we do need to look at a more complicated one where we have to use logarithms. And the other thing that you need to know is that sometimes your problems, when you start the limit, they're not in the form 0 over 0 or infinity over infinity, but you can convert them to be in that form. Okay? So that's what we want to take a look at. What time do we get out of here?
40?
What time is it?
You have 20 minutes.
Perfect. Okay.
Dang, you are out of bolts. Dang.
If they're
I
not in
know.
the form
Got a
0
lot
over
to do.
0, what else could they be in, like 0 over 1? Or...
It could be any of those other ones that I wrote
Those
down at the
other-
beginning of your notes, like 1 to the infinity or 0 to the 0, those.
Couldn't you just plug in the... Okay, cool.
Okay. Yeah, I think you'll see in just a second. Okay, so let's do this problem. The limit as x approaches 0 of e to the 3x minus 1 over x. Okay, so I'm working my AP practice test. I'm going along and I see a boom limit problem. Okay, first thing I'm always going to try is
Plug
Plug it in.
Direct substitution. If I substitute directly into this, I get what? 0 over 0. Right? That tells me that I can do what? L'Hopital's rule. So I'm going to have the limit as x approaches 0 of, what is the derivative of the numerator? 3e to the 3x over, what is the derivative of the denominator? 1. Can you plug in now?
Yes.
Yes, and what do you get as your answer? 3. So there is an example of one of a limit problem that you could not have done using an algebraic technique. Okay.
What if it's just b to the x? Actually, no, you get 1 over 1.
Okay. Limit as x approaches negative infinity of x squared over e to the negative x. Not that. Okay, the limit as x goes to negative infinity of x squared over e to the negative x. So what do you get?
Infinity
Infinity
over
over infinity, right? Okay, that's an indeterminate form that allows me to use L'Hopital's rule, right? Okay, so this now becomes the limit as x approaches negative infinity of 2x over negative e to the negative x. Now what do you get? I get negative infinity over negative infinity, right? Which says that I can do it again. Okay, derivative of the numerator is 2. Derivative of the denominator is e to the negative x. So what is the answer? 2 over infinity, which is 0. Okay. Raphael, you with us? Try to hang with us. We're doing some problems now.
That was right.
Okay. So now we need to look at sometimes we must change problems into the form 0 over 0 or infinity over infinity. Okay, by rewriting them. Sometimes we must change problems into the form 0 over 0 or infinity over infinity.
If it's oscillating, you just, the limit is like, what is oscillating?
Right.
Like on the sine curve, and
Yeah.
it's going to infinity, it's oscillating 0, so the limit would be 0.
Well, it depends on where you're, like if you're doing it as x goes to infinity, that one doesn't exist. I don't know if that's what you're asking me or not. Okay. All right, what happens here? Is this in the form 0 over 0 or infinity over infinity right now? No. But I can make a really simple move by doing what?
moving to the negative x.
That, right? because e to the negative x is the same as 1 over e to the positive x. Now, if I do that substitution, I get infinity over infinity.
Do we have to put the limit as x approaches infinity every time?
You should at least do it for the first one, like whenever you rewrite it. Okay, so now I can start to use L'Hopital's rule, right? So derivative of the numerator is,
1/2. X to the negative 1/2.
right, that over that. This is the same as that, right? I can move the e to the x up with all of this stuff. So what does this go to? 0. Did you have a question, Jenny? Okay. This right here, all I did was move it right there. All right, let's do one more. It's a little bit harder, and then we'll do the one that requires logarithms. So I'm going to do the limit as x approaches 1 from the right of 1 over ln x minus 1 over x minus 1. And by the way, why do I have going at 1 from the right? Why?
Because you can't take,
It doesn't work for Ellen. There's
yeah,
Yeah, because of that right there, right?
you can't have anything less.
Okay. All right, so if I plug that in right now, what do I get? I get 1 over something approaching 0, which turns to... I would suggest that you engage your brains, okay? Because I'm looking out there, and there's maybe a couple of you that are actually have your brains engaged and you're thinking through this. The others, you're just waiting for me to tell you, okay? You're just waiting for me to tell you. These questions are going to come up on the AP test. You have to be able to think through growth rates. You have to be able to tell me what 1 over ln x as x approaches 1 from the right is approaching. You must be able to do that. So please don't stare at me with your mouth open, waiting for me to tell you the answer. Engage your brains and try to think, okay? I'm not trying to be rude, but I have to clue you in because some of you are just like, you're done, you're waiting on Friday. I get it, I'm waiting on Friday too. I need it just like you guys do, okay? But let's try to be engaged and think. So if I'm approaching, the denominator is approaching 0 from the right. So 1 over a denominator that's approaching 0 from the right is going toward infinity. Thank you. Okay, infinity. Minus, what's this one going toward? You have a question, Isaiah?
Oh, yeah, you said it was approaching 0 from the right.
Okay, thank you. 1 from the right.
Okay.
What's this one going to? I meant the, I'm sorry, I meant the final answer. That's fine. We're good. And this one is also infinity, right? So, infinity minus infinity is an indeterminate form. But is it an indeterminate form for which I can use L'Hopital's rule? No. So what do you suggest I do?
Are you
Okay.
or negative?
You get a common denominator.
I need a common denominator. Good, Ryan. I need a common denominator. Because that common denominator is going to create a single fraction, right? Common denominator will produce a single fraction. And then I can look for that 0 over 0 or infinity over infinity thing. So Ryan says I need a common denominator, and that common denominator will be ln x, x minus 1. So this numerator becomes what?
X minus 1.
X minus 1 minus
ln x.
ln x. Now, if I plug in limit as x approaches 1 from the right, what am I going to get in the numerator? 0, right? Because this one is approaching 0 as I go at 1 from the right, and 1 minus 1 is 0. So this is 0 over 0. Now can I use L'Hopital's rule? Yes, now I can use it to help me figure out this limit. So I'm going to have the limit as x approaches 1 from the right. What is the derivative of the numerator? The derivative of x is 1 minus derivative of 1, 0. What's the derivative of ln x? 1 over x. All over. What are you going to have to use in the denominator? Product rule, right? The product rule. So the first times the derivative of the second is 1 plus the second times the derivative of the first, which is 1 over x, right? Okay, so can I substitute yet? No, because this still gives me 0. That's 0 plus 0. So I still have 0 over 0, right? So I'm doing it again. Limit as x approaches 1 from the right. What's the derivative of the numerator?
X over, or 1 over x squared.
Positive 1 over x squared, right? Positive 1 over x squared. Because if you're thinking about that, negative 1 over x is the same as negative x to the negative 1. So negative times negative is positive. Okay. And then on the denominator, derivative of ln x is 1 over x. I'm going to convert this to 1 minus 1 over x, right? That's what it equals. Right? X over x is 1. So the derivative of 1 is 0. And the derivative of this one's going to, again, give me what?
1 over x.
Plus 1 over x squared. Now can you plug in the 1? Yeah, what do you get in the numerator? 1. What do you get in the denominator? 1 plus 1, right, so 1/2.
Can you separate the limit from the beginning and work with them individually? Does it work like that? Or is that just
Yes, but you're still going to get infinity minus infinity. You see what I'm saying? Like, that one's infinity, and that one's
But you
infinity.
can work with them separately and then get a number minus.
Well, it's 1 over infinity, and that isn't an indeterminate. That's 0. No, it doesn't get you anywhere. You're just left with like indeterminate form after indeterminate form. Yes.
How would 1 over x minus 1 approach infinity?
How does
The 1 over x
1 over x minus 1? You're going at 1 from the right. Right? So we're talking about a number like 1 point. Right? So now I have 1 over, right? Which is like 1 over 1,
Oh, okay.
right? And then when you multiply by the reciprocal. Okay. Okay, last one. Sometimes we must use logarithms in order to evaluate limits. So if I start with some sort of direct substitution, I get 1 plus 2 over infinity. 2 over infinity goes to what? 0. And then, so I end up with 1 raised to the infinity power, which is an indeterminate form. Okay, in mathematics, that's an indeterminate form. So clearly, what's jumping off the page at you? Where do we have a variable? In the exponent, right? We've got a variable in the exponent. We never want variables in the exponents, okay? And that's why we have logarithms, right? They help us get them out of exponents. So here's what we're going to do. We're going to let y equal the limit as x goes toward infinity of 1 plus 2 over x to the x. And we just said that this gave us 1 to the infinity, which I know is indeterminate. Okay, so what can I do now to both sides so that I can get that x down? I can ln them, right? So I can say ln y. Yes?
Just FYI, you have like about 2 or 3 minutes left.
Thank you. I forgot my limit. Hang on. Okay, so I ln this, which allows me to bring the x down in front.
Can you just assume the inside's going to give you 1 and just leave it as 1?
No. Because right now I'm of the form infinity times 0, which is still indeterminate. Okay?
Is there like a verb for took the natural log of? Or is there a rule?
I
To log
don't think so.
natural log is? To bring the derivative to.
Okay, so ln y is equal to, now I need a common denominator in the numerator. Actually, here, I need this x to go somewhere.
Divide by x.
I can't divide by it, but I can divide by 1 over it. Right? Isn't dividing by 1 over x the same as multiplying by x? So this is an equivalent state. This says ln. Oh, did I lose my limit again, though?
Yeah.
I lost my limit. Here's my limit.
It's like when you lost a nine.
Okay? So now I have what? Now what form am I in? 0. Now I'm in 0 over 0, right?
Yes.
Yes. So now I'm in 0 over 0. So now I can start the process of going through L'Hopital's. I'm going to give you this. I'm going to show you, there's going to be a bunch of steps in here that are missing, but I want to show you this last thing here. You will get ln y is equal to 2. Translate that for me. E squared equals y, right? Okay, so there's a bunch of steps in here that are missing where we actually use L'Hopital's, but I wanted you to see how you convert it. Okay, I have a worksheet for you for homework.